4,500 years ago on the Nile, shipbuilders faced a paradox. To survive the sea, a vessel had to be rigid enough to hold tons of cargo, yet flexible enough to twist with the waves. Iron rusted, copper bent, glue dissolved. Yet ancient engineers built ships that carried hundreds of tons across open ocean and grew tighter the longer they stayed at sea. They didn't fight the water. They used it. Modern ships are built like skeletons. A steel frame carries the load, and the outer hull just keeps water out. Ancient Mediterranean builders did the opposite. They built the skin first. No internal frame, no skeleton. The hull itself carried the stress. Every plank bore load, every joint locked under pressure. This shell-first method turned the entire ship into one continuous structure, something closer to an aircraft fuselage than a wooden raft. And it worked because they understood something modern builders often forget. Wood isn't passive, it reacts. Section 1. The sewn ship. Before the perfected joint came rope. Early Egyptian shipbuilders drilled angled channels into cedar planks, but never all the way through to the outside. The rope stayed hidden, protected from seawater. Through those channels they threaded twisted halfa grass rope. When pulled tight, the rope compressed fiber wadding between the planks. Papyrus, linen, plant fiber. The result? A hull that flexed instead of cracking. When waves struck, the ropes stretched slightly. The fiber compressed. The planks shifted microscopically. The ship absorbed energy instead of shattering. It behaved more like a suspension bridge than a rigid box. But rope rots. It stretches. It needs maintenance. For long campaigns and heavy trade routes, they needed something permanent. So they replaced rope with wood itself. Section 2. The mortise and tenon. The breakthrough was the mortise and tenon joint. Each plank edge was carved with a rectangular slot, the mortise. Into it went a hardwood tongue, the tenon. When the next plank was added, it slid onto the exposed tenon, locking the boards together in perfect alignment. But alignment alone isn't strength. So builders drilled a hole down through the plank face into the buried tenon. Then they drove in a hardwood peg, a tree nail. Here's the genius part. Often the hole in the tenon was drilled slightly off-center. When the peg was hammered in, it forced the tenon sideways, pulling the planks tightly together. This created constant internal compression. The joint wasn't just connected, it was under tension. On a large Roman cargo ship, this was done thousands of times. Thousands of hand-cut joints, thousands of pegs. The hull stopped being a stack of boards. It became one continuous, tension-locked shell. Section 3. Shell-first construction. This method shaped how the entire ship was built. The keel was laid. Then plank after plank was added upward, each one locked to its neighbors. No ribs at first. Just shell. Only after the hull shape was complete were the ribs inserted, shaped to fit inside the finished form. The ribs weren't the main structure, the hull was. Engineers call this a monocoque design, a single shell that carries its own load. When these ships ran aground or hit heavy seas, the force spread across the entire hull instead of snapping individual boards. But even with perfect joints, microscopic gaps remained. And that's where the real trick began. Section 4. The hydro-expansion seal. Wood absorbs water. When it does, it swells, mostly across the grain. When a new ship launched, it leaked badly. Crews bailed constantly for hours. That wasn't failure, it was part of the process. As seawater soaked into cedar planks, oak tenons, and tree nails, the wood expanded. The planks pressed harder together. The tenons swelled tighter in their mortises. The pegs increased clamping force. Within a day, the seams crushed themselves shut. The ocean sealed the ship. Iron nails rust and destroy surrounding wood over time. This system did the opposite. The longer it stayed wet, the tighter it became. The sea wasn't the enemy. It was the locking mechanism. Conclusion. If this system was so advanced, why abandon it? Scale. A mortise and tenon hull required thousands of hours of skilled labor. Every joint was hand-cut. Every peg custom fit. As Rome expanded and needed hundreds of grain ships per year, speed mattered more than elegance. Joints became fewer, tenons smaller. precision reduced. Eventually, skeleton-first construction replaced shell-first entirely. It was faster, cheaper, easier to mass-produce. We traded material intelligence for production efficiency. But for over 1,000 years, Mediterranean ships didn't just resist the sea. They partnered with it. They were machines that came alive in water. And that might be one of the most overlooked engineering revolutions in history.